Okay, thanks. So thanks for the invitation. So I have to apologize for a few things before starting. So first, I'm sorry I was not able to provide the nice written notes. So sorry, time was too short. So maybe you can have scanned versions of my personal notes, which are maybe usable, maybe not. I don't know. So that was the first apology. Second apology, which is more important. So I'm certainly not an expert in arithmetic geometry at all. Okay, so I come from dynamical systems. So I will do my best not to say too many mistakes in arithmetics, but I apologize in advance if I say something wrong about heights or whatever notion I don't really know. So I want to give you some flavor of this field of arithmetic dynamics, which is at the borderline between, well, arithmetics and dynamics, right? So it's about, on one hand, algebraic dynamics and holomorphic dynamics, and say number theory and arithmetic geometry. So I will try to focus, because this is what I understand, on the dynamical side. Okay? So most often when there are some statements, there is some arithmetic part and some dynamical part. I guess that most people in the room prefer or understand better the arithmetic part, but it's not my case. So I'll try to explain how the dynamics enters the story. And so there is a lot of material, so the lectures will be somehow less precise than, for instance, the one of Pascal. At some moments, it will more look like a seminar talk, okay? So my plan, which is not completely fixed, is this one. So in lecture 1, I want to do kind of a crash course in holomorphic dynamics on the sphere. On P1, that would be also some non-Archimedean stuff, plus a few consequences of equidistribution. So some first consequences of equidistributions. So there's another disclaimer here. So I think Antoine did not state the arithmetic equidistribution theorem now, and also Pascal. So I will rely on some theorems, which I will use as a black box, which will be explained in Antoine's talk and maybe in Pascal's talk too. Okay? So this is true. Lecture 2, I want to talk about parameter spaces questions. So the kind of arithmetic questions you find when studying families of dynamical systems. So it will be about families of dynamical systems. And actually, I have quite a lot of things to say in this lecture 2, so maybe it will also cover part of the lecture 3. And lecture 3, I would like to talk, so depending on the time I take to discuss this, I would like to talk about the dynamical Manin-Mumford problem. So as I said, this will certainly cover a little bit of lecture 3 too. Okay, let's go. So today, I want to give you some general ideas of holomorphic dynamics. So again, I will not be able to give complete proofs because I will cover a lot of different things. Okay, so first, let me remind you a few. So for the moment, we work on the Riemann sphere. So let me recall first a few useful tools from complex analysis. So the first thing I'll need is the uniformization theorem. So which is due to many people, but certainly we should cite the name of Poincaré and also Koebe, which says the following. If you take a Riemann surface, a smooth Riemann surface, which is simply connected, then you have only very few choices. Then either S is the unit disk in the plane, or it is the plane itself, or it is the Riemann sphere. So disk, the plane, or the sphere. Okay, and now if you take any Riemann surface, so if now S is any Riemann surface, you can consider, you fix a base point. It's not the, you choose your favorite base point, and you consider the universal cover. It will belong to one of these three types. So you have three possibilities. So either it is the disk, or the plane, or the sphere. So if it's the disk, we say that S is hyperbolic. If it is the plane, you say that S is parabolic. And so now the suspense is terrible. If it's the sphere, you don't say anything. Okay? So here you have no name. You have no name because the only possibility is that S is the sphere. Okay? S is the sphere. Okay, and in particular, elliptic curves are parabolic. Okay, so it may be not so a good idea to call parabolic the elliptic the sphere here. Okay, so you have to think about this as hyperbolic as being the generic situation. So in a sense, it is the generic case. Of course, it has no proper mathematical meaning, but maybe it's useful to think about it as the generic case. Okay. So for instance, if you take an elliptic curve over C, then it is biholomorphic to C over some lattice. So you see that the universal cover is C. It's parabolic. Okay. An important result, theorem, which is maybe Montell theorem, I don't know. So if you take three distinct points in the sphere, if A, B, C in the sphere, so, okay, I'm going too fast here. So P1 of C is, as you know, the one-point compactification of C, okay, as a topological space. And as you certainly know by stereographic projection, this is the same as a manifold, it's a sphere, right? As a topological manifold, it's a sphere, but also as a complex manifold, it's a sphere because you can make this stereographic projection with two charts. Okay, so that's the Riemann sphere. So if you take three distinct points, on the sphere, then the sphere minus the 3 points is hyperbolic. Okay, so the complement of 3 points. So the complement of 2 points, I should have said, the complement of 1 point in the sphere is the plane, so it's parabolic. The complement of 2 points is C star, okay, which is isomorphic to C over C, C over Z by the exponential. Okay, so that's the sphere minus 2 points, and when you go to 3 points, you have something which is a hyperbolic Riemann surface. And the proof is not complicated. the proof. So again, you fix a base point, which is different from these 3 points A, B, C. Then the fundamental group of the sphere minus 3 points based at this point is free on 2 generators. Okay, when you look at the plane, so that's the plane minus 2 points. You have 2 different paths. So that's the base point somewhere. What's the you have a base point somewhere. You have 2 different paths going around 0 and 1, and these 2 paths generate a free basis of the fundamental group. Okay, so the fundamental group of this surface is free on 2 generators. Now let's call it S. Now the universal cover of S, so is either C or D. It cannot be, of course, it cannot be it cannot be the sphere, because if a manifold has a compact fundamental group, then it is compact too, because just by surjection, right? So it is either this or that manifold, and the fundamental group of S acts on the universal cover discretely by automorphisms. Okay, now we know all the automorphisms of the plane. The holomorphic automorphisms of the plane is the same as the affine mappings. Set of form AZ plus B with A in C star and B in C. Okay, and now this group is nilpotent. Okay, because the commutator of 2 elements goes in a if you take a commutator of affine transformation, you fall into the group of homotheties, which is abelian. So this group does not contain a copy of the free group on 2 generators. Okay, the group is too small. So you have no choice.
Why is C X by B holomorphic?
This is because you're on a Riemann surface, and when you have the universal cover, locally the structure of the universal cover is exactly the same as you transport all the structure of your surface, right? And this deck transformation, they preserve all the geometric structures you have, in particular holomorphicity. Okay? Okay, so the universal cover must be the plane, cannot be the plane, so it must be the disk, and that's the end of the proof. Okay, so an important consequence of this. So a corollary of this, let me restate it. If omega is a domain in the sphere such that the complement of omega has at least 3 points, then it is hyperbolic. It's a trivial consequence of the result here. Okay. Another important result, which is of course related to this one. So let me recall a definition. Let me recall what a normal family of holomorphic functions is. So I will consider normal families of mappings from a certain domain in the sphere to the sphere. So if you take a sequence of meromorphic functions, so a map from a domain of the sphere to the sphere is just a meromorphic function, right? So if you take f a family f of meromorphic function is normal if and only if it is pre-compact for the topology of uniform convergence, of local uniform convergence. Okay, meaning that from every sequence, you can extract a subsequence which converges uniformly on compact sets. Okay, and every time I will say normal family in this talk, it will a normal family of mappings into the sphere. In particular, if you converge to infinity, for instance, converging to infinity is being normal. Okay, so theorem. So Montell theorem. If you take any domain, in the sphere, and you take any family of meromorphic mappings, and F is a family of meromorphic mappings, so from omega to the sphere, which avoids 3 points, then it is a normal family. Okay, so it's a very strong compactness result for sequences of holomorphic functions. Okay, all you need to do to have compactness, so it's very important in one-dimensional holomorphic dynamics. All you need to do to have compactness is to avoid 3 points, which is a situation, you will see in examples, that is a situation which is quite common. Okay, so the proof is obvious, just a simple consequence of the previous statements. So the proof. So it's a local statement. It's a local theorem. So we just need to prove it on the disk. So pick a disk D in the domain. And now you have a family of meromorphic. If you take F in your family, you can restrict it to the disk to get a family, to get a function, a meromorphic function from this disk to, say, C, or the sphere, minus 3 points. Okay, now the disk is simply connected, so you can lift it to the universal cover. So that's the universal cover. And so there's a lift like this. So you can locally lift your family of functions to a family of functions to the unit disk. And now, if you have a family of functions from any disk or any domain to the unit disk, it is compact just by the Cauchy estimates and the Arzela theorem. And now the set of lift. So of course there are some choices here, right? I don't want to be too precise, but to have a lift, you must fix base point on the space, you must fix base points, okay? I don't want to enter into details, but the family of lifts now is compact because of just the Cauchy estimate. So the Cauchy estimates give you for free an estimate on the derivative of a function with value in the unit disk, and the classical Ascoli theorem. Okay, so this proves the result. Okay, last tool that we will need. So last important tool is the hyperbolic metric. So if you want, if you want to understand what a hyperbolic metric is, all you need to know is the Schwarz lemma. So remember the Schwarz lemma. The Schwarz lemma says the following. It says that if you take a holomorphic function from the unit disk to the unit disk, such that it maps 0 to 0, then you have a control of the derivative at the origin. Then the derivative at the origin is not greater than 1, and it is equal 1, it equals 1, if and only if f is an automorphism of the disk. So that's what the Schwarz lemma says. Okay. Now we know all automorphisms of the disk. So now if you take any map from the disk to itself, let's say a map which sends this point here alpha to a point beta. Since we know all automorphisms of the disk, you can always map this disk. You can take an automorphism H alpha which maps alpha to the origin here. So it's an automorphism of the disk. Okay. Take an automorphism H beta which maps beta to the origin. And now you have a composite mapping. So if f of alpha is equal to beta, then when you do H alpha inverse f H beta, you can it maps the origin to itself. So you can apply the Schwarz lemma. So you can apply the Schwarz lemma to this map. And also let me recall that this H alpha is given by an explicit formula, which is z minus alpha over 1 minus alpha bar z times some rotation term which does not impact the derivative. Okay? So you can apply the Schwarz lemma to this map, and this gives you the so-called Schwarz peak lemma. Which I will not state by a formula because it's a formula which is a little bit complicated to write down. But it says that f is a weak contraction in this sense relative to a certain Riemannian metric. And the Riemannian metric is this one, so-called Poincaré metric in the disk. So I never remember if there's a square in the denominator. So there's no square in my note, but there might be a square downstairs. It's not important. So there is a certain Riemannian metric on the unit disk, and every mapping from the unit disk to itself is a weak contraction for this Riemannian metric. Okay? And if it is not an automorphism, then it is a strong contraction, meaning that the inequality here is strict. So that's a fact. And let me continue here. Last comment. So now if you have any, now if, so last situation, if f is a mapping between, a holomorphic mapping between hyperbolic Riemann surfaces, then you can define, so that this so-called Poincaré metric, or hyperbolic metric, so that's the Poincaré metric. Then you can define the Poincaré metric on S1 and S2 just by going to the universal cover. So the Poincaré metric can be defined on S1 and S2 because, as I said previously, the structure of S is locally isometric to that of its universal cover. The deck transformation preserves all the structures, in particular the Poincaré metric. So you can define the Poincaré metric on S, and then F is also a weak contraction. And F is a weak contraction. And strong if it's not an automorphism. Okay, so that's for the tools we will sometimes meet in the lectures. Okay, so let's go to holomorphic dynamics now. So that's section 2. A few facts. I don't know, basic facts. Actually, not so basic on holomorphic dynamics on the sphere. So now, I will take a rational map from the sphere to itself. So it is just defined by a rational function. I will normalize the polynomials so that they have no common factors and of degree d. The max of the degree of P and the degree of Q is D. And so it might be that F is a polynomial. So maybe, maybe Q is 1, which is a very interesting case which we will discuss a number of times. And I want to consider this mapping as a dynamical system, okay? So I will iterate this map, and I want to so the basic problem of dynamical systems, as you know, is you take a point. So dynamical system mean that I want to understand the behavior of the composite iterates when n is bigger than 1, meaning that I take an initial point z0, and I look at the sequence defined by this simple recursion formula, and I want to understand the behavior in terms of z0. So I want to understand the sequence Zn, depending, of course, on the initial value, which is the basic problem of dynamical systems. Let me already say that I will always assume that the degree is larger than 1. Okay? When you in degree 1, you can classify everything in the dynamics is not very interesting, not very complicated. Okay, so I want to understand these iterates here. So it's a n-fold composition product. Okay, so the first definition is the Fatou-Julia dichotomy. So you say that a point is Fatou. So Z is a Fatou point, Z0 is a Fatou point if there exists some neighborhood of Z0 such that the family of iterates restricted to this neighborhood is normal. And otherwise, you say that otherwise Z0 is Julia. Is of Julia type. Okay, so you get normal families in the sense of compact family of meromorphic mappings. Okay, which was defined just before. Okay? So you get a decomposition of the sphere. You get a decomposition of the sphere as the Fatou set and the Julia set, so the set of points of Fatou type and the set of points of Julia type. And by definition, the Fatou set is open. And so that's a disjoint union, okay? And this one is closed. So you have an open set where the dynamics is locally. So what does it mean to be normal? To be normal, it's equivalent to say that it is equicontinuous. Okay, for the spherical metric. So it means that there is no sensitive dependence to initial conditions there. If you start close to Z0, well, so if Z0 prime is close to Z0, then the iterate is close to the iterate of Z0. So there is no chaotic behavior here. And on the opposite, on the Julia set, you have this sensitivity to initial conditions. Okay. So what can it be said on these sets? So remember Montell theorem, which is not on the blackboard anymore, but by Montell theorem, if Z belongs to the Julia set, so I will denote this by F and the Julia set by J. So if Z is in the Julia set, then for every neighborhood of Z, the sequence of iterates, which is not normal, avoids at most 2 points, 3 points, 2 points. Okay, because otherwise it would avoid 3 points, and then it would be a normal family. Okay, so it means that if you look at the union of the iterate of this neighborhood, then this set is P1 minus something, maybe. Let's call it EZ. And EZ contains 0, 1, or 2 points. Okay? So there's a little proposition here, which I will not prove. Very easy proposition. So this set EZ does not depend on Z. Okay, so I will call it E. And this is the so-called exceptional set. So the exceptional set is a set of points that you avoid when you start from the Julia set. And it is, excuse me? Of the fact that it does not depend on Z? I will give the idea. And E, I will give the idea just after. So if E, this E is characterized by two facts: the fact that it is a finite set and the fact that it is totally invariant, meaning that if you take the preimage of E, then it is equal to E, or maybe contained in E is enough. Let's say equal is the same. Okay? So if you take any finite set which is totally invariant, then it is the exceptional set. And also, let me give the idea of the proof. So if you take any point Z, if you take any point Z and define EZ like this, then I claim that this set EZ, by definition, is totally invariant. So if you take any point z and define EZ like this, just by definition here, it is finite because of Montell theorem, and it satisfies this equality. Actually, it satisfies this. Okay? And now I claim that any set satisfying this, let me call it star. So the claim that if E satisfies this star, then the cardinality of E is less than 2. And the proof is not very complicated. It is because if it is totally invariant, it means that F maps C minus E to C minus E. Just by assumption of total invariance, it implies that F does this. And then you just apply the Riemann-Hurwitz formula with some degree here. You apply the Riemann-Hurwitz formula, which says that the Euler characteristic of C minus EZ, sphere, excuse me, it's not C, it's a sphere here. It must be equal to the degree times the same Euler characteristic minus a ramification term. Okay, so this implies, so you put the R on the other side, this implies that and this is bigger than 2, that the Euler characteristic is non-negative. Okay? But this Euler characteristic is just 2 minus, so it's the cardinality of is the characteristic of the sphere minus the cardinality of E. So it is 2 minus the cardinality of E. Okay, so you get that the cardinality of E is less than 2. Now, why it does not depend on Z? Because if you take any 2 points, if you take any 2 points, you take the union of the corresponding exceptional sets, it is also an exceptional set. So as soon as you take several points, because you know there's a universal bound on the cardinality, then with a few arguments you get this independence here. Okay. So there's a fact. So if the exceptional set has maximal cardinality, so cardinality 2, then it's a very special case. It means that F is conjugate.
Sorry.
Yes?
Why is the D more than 2?
Because it's an assumption. It's a degree of the map. So we take a rational map of algebraic, okay, we take a rational map of algebraic degree at least 2. That's the assumption for all the talk. But this algebraic degree is the same as the topological degree, the number of preimages of a point. Okay? When you solve this equation, P of Z over Q of Z equals W, you get D solutions. Okay, not generically, you get D solutions. Okay, so that's the D here. Okay? Okay, so if the exceptional set has cardinality 2, then actually F is conjugate to a monomial, ZD or Z minus D. So that's a very special dynamical system. You can forget about it. So in practice, this case never happens. So if now the cardinality of F is equal to 1, then you can always conjugate so that the exceptional point is the point at infinity, and then F is a polynomial. So it's equivalent to say that F is conjugate to a polynomial. And E in this case, of course, is the point at infinity. And the generic case, well, I don't have to say anything. The generic case, the remaining case, is the case where the exceptional set is empty. Okay.
Sorry.
Yes?
F is conjugate or what's
By a Möbius transformation. So it's a conjugacy in the automorphism group of P1, which is a space of Möbius transformation. Okay? Okay. Consequence of all this. So a corollary of this if you take any z in the Julia set, if you take n a neighborhood of z, and you take the union of the forward iterates of n, so we said that it is P1 minus a finite number of points, so certainly it is dense in P1. If you take the closure, you get P1. So that's a trivial consequence of the previous statement. And also an interesting corollary is that if the interior of the Julia set is non-empty, so remember the Julia set is a closed set and the Fatou set is an open set. If the interior of the Julia set is non-empty, then actually the Julia set is equal to the sphere. And now I remember I forgot to say something. This is because, indeed, by definition, the Fatou set and the Julia set are invariant by the dynamics. So they are forward invariant. And also backward invariant. So we say totally invariant. Okay? So that's just a simple consequence of the previous corollary, right? Because you take a neighborhood which is contained in the Julia set, you take forward images, and it fills everything, but it still contains the Julia set. So it means that the Julia set is everything. Another corollary here is that if you take a non-exceptional point, you take a point which is not exceptional, and then you take pullbacks. You take preimages. So you take preimages of this point z by Fn, and you take the union over all n. So you take the full tree of preimages of this z, and you take the closure of this. So then it contains the Julia set. Why? Well, you just have to look the first, you just have to look this here again. So now we know that there's no z here. If you take any point, and if you take any point, maybe let me call it w. Here, the proof here. So let z any point in the Julia set, and you must prove, we have to show that the preimages of W accumulate Z. That for every neighborhood of Z, there exists some n such that a preimage of W intersects n. Okay, but that's the same as saying that the image of n contains W, which is just the definition of being non-exceptional. Okay, so it's just reversing the time. So here you have a statement in forward for forward iterates. When you reverse the time, you get this. So if you take any non-exceptional point, then its pullbacks accumulate the Julia set. So there are a few consequences of this. So corollary of the corollary. The Julia set J is an infinite set. Because you take any point in J, let W now belong to the Julia set, and not, okay, you have to prove that it is, okay, sorry, I'm going too fast. You have to prove first that it is non-empty, which is very easy because we have assumed that the degree is larger than 1. So when you iterate forward, the degree grows, so you can have a normal family on all the sphere. Okay? So the Julia set is non-empty, and then you have to show that it is not contained in the exceptional set, And if you look at the classification of possible exceptional sets, you see that every time an exceptional point is contained in the Fatou set. I will come back to this point later. So it is obvious that there exists a point outside, and then the union of all preimages of this point, take the closure, it is the Julia set. So it is infinite, and it is the closure of these preimages here. Okay. Basic question. So what does G look like? So I have this closed set on the sphere, which is the set of points where the dynamics is complicated. So a first possibility is that J is the sphere itself. So it's very common, actually. It happens very often that the Julia set is the whole sphere. Okay, so now you know what it looks like. Second possibility, J is a curve. Say a smooth curve, C1 curve. Okay? Then you can also classify all the possible situations. And it implies that actually this curve is a circle. So circle in the spherical sense, so meaning that a line is also a circle. Okay, so of course there's a little bit of work here, but it's not very difficult. And actually we can classify all the possibilities. So it can be a segment in the real, and then it implies that actually f is a Chebyshev polynomial. Or it can be a circle, an actual circle. It can be an actual circle, and then f is a Blaschke product. So, of course, you don't have to remember all this list. What is important is if the Julia set is a curve, then f is special, in a sense. And otherwise, J is a fractal set. Okay, it's a complicated fractal set. So besides this very specific case, so this one is not specific. As I said, this is very frequent. But besides these cases, J is always a fractal set, which will sometimes play an important role in these arithmetic dynamics questions. Okay. Let's say a few words about periodic points. So Z is periodic if Fn of Z equals Z for some n. Okay, and the smallest such n is the period. So when you have a periodic point, the important quantity is the derivative at this periodic point, which is called the multiplier. So it's called the multiplier. So you may ask, what is the meaning of this derivative since I'm working on the sphere? But it's not very important because since f is mapping a point in the sphere to itself, it maps a certain tangent space to itself, and the value of this multiplier does not depend on the choice of a Riemannian metric. Okay, so you can put the derivative in any coordinate, and you get this number, which does, let's say, for spherical metric, but it is not important. Okay, then you have three cases. First case, the multiplier is smaller than 1 in modulus. Then the point is attracting, and Z is an attracting point. Is attracting, so let's say Z is a fixed point. There exists a certain neighborhood of Z which is mapped into itself by the picture is ugly. Maybe I should. So you have a certain neighborhood which is mapped into itself by the dynamics, and everything converges, everything in this neighborhood converges to this point. Okay? Then in particular it belongs to the Fatou set. Okay? It may be that this derivative is equal to 0, for instance. So example, if f is a polynomial, and you look at the point at infinity, you can do this very simple calculation. In this case, the multiplier is a fixed point, and the multiplier is equal to 0. So it is a super attracting point. It attracts all the points in the neighborhood. And Z is the point at infinity, is an attracting point. So other possibility, this multiplier is bigger than 1. So this is a repelling point. Okay, so the picture is the opposite as this one. So in particular, this repelling point, if you calculate the iterated derivative at this point, you get a sequence of complex number which goes to infinity. So it belongs to the Julia set. Okay, the iterated derivative grows exponentially. And the remaining case is the case of neutral points. So these ones which are neither attracting nor repelling. Last case, neutral point. So the classification of neutral points is quite complicated. Sometimes they are in the Julia set, sometimes in the Fatou set, and there is no general result. Okay, it's not easy to understand exactly. Well, it's complicated. Okay, so we don't have to. I don't want to talk about this.
Is it the case, for example, that like if you have an attracting point set and there exists some small neighborhood such that all the other points in the neighborhood are equal, or?
Why? I mean, okay. If you take a point here, what happens to him? What happens is that it will converge to this point here. Okay? So it will never be periodic. So it has a whole neighborhood which is free of periodic points. Okay? And it is not true for repelling point, which is, I will just state it right now. So there's an important theorem by Fatou, which says that the Fatou set, the Julia set, is the closure of the set of repelling periodic points. So if you take all repelling periodic points and you take the closure, you get the full Julia set. So meaning that these repelling points, they have plenty of other periodic points in the neighborhood. Okay? So I will not prove it right now, but I will give you a number of ideas which ultimately will lead to a proof of this theorem. So it's an important idea in one-dimensional dynamics that most periodic points are actually repelling. So there's another theorem by Fatou. I mean, everything basically is due to Fatou here, so I will not write Fatou 20 times. So every attracting periodic orbit attracts a critical point. So if you have an attracting point somewhere, let's say it's a fixed point. So let me make the proof.
What do you mean by critical point?
A point where the derivative vanishes. prime of Z equals 0. So take an attracting periodic orbit, a periodic point Z, okay, and denote by B its basin, let's say immediate basin. So what is B? B is the connected component of Z. So you have, the basin of the basin. It is the set of Z prime such that, let's say it's fixed. Assume Z is fixed and attracting. And if it's not fixed, you just replace F by an iterate so that it becomes a fixed point and attracting. So you introduce the basin of attraction. So you introduce the basin of attraction, which is a set of points which converge to Z under iteration. And let's say B naught, it is the connected component. So that's an open set, which may be disconnected. Okay, maybe you have plenty of components, and it's always the case. You have plenty of components which are mapped, well, it's not connected, sorry. And B naught is the connected component of Z in the basin. It's a so-called immediate basin. So you have Z, and there is a certain open set around, a maximal open set, where the points converge to Z. Then it is obvious from the definition that F maps this immediate basin to itself. Okay?
Is basin open?
Yes. It's open. That's an exercise. It is open, not difficult. Good question. Okay, so F maps B naught to itself, and also this basin is disjoint, of course, from the Julia set, because all the points in the basin are Fatu points. So in particular, this B naught, it avoids infinitely many points, so it is hyperbolic. So it's a hyperbolic Riemann surface. Now assume that there is no critical point in B naught. Then if there is no, so let me call it a critical set. Let me denote it like this, crit. So if the critical set is disjoint from B naught, then it implies that F from B naught to itself is a covering. Okay? And if it is a covering, then it must be a local isometry for the Poincaré metric. Okay? But it is not possible because everybody is converging to Z. So you must have some contraction. Then you get a contradiction here. Okay, so every attracting orbit attracts a critical point. Now, a consequence of this is that the number of attracting cycles, so cycle is just another name for periodic orbit, is bounded by the cardinality of the critical set, which is 2D minus 2. Counted with multiplicity. Okay, so you see that among all, okay, I should have said before that there are infinitely many periodic points because the number of periodic points of period n, I'm cheating a little bit here, is d to the n plus 1. So you solve the equation Pnz equals z over Qnz equals z. That's an equation of degree d to the n plus 1, sorry. Like that. So you have infinitely many periodic points. So I'm cheating a little bit here because there's a question of multiplicity, right? But think about it. There are infinitely many periodic points, which actually follows from this. And among these infinitely many periodic points, you have only finitely many attracting points. And a more complicated theorem, again by Fatou. Yes? Actually, it is equal if you count multiplicities, but if you count, okay, if you count it as a set, you're right. If you count multiplicities, for a polynomial, infinity is a critical point of multiplicity d minus 1. Okay, but as a set, you're right that I must write an equality. So there's a theorem by Fatou. Actually, you can, most periodic points are repelling in the sense that the number of non-repelling cycles is also finite. So the bound of Fatou is 6d minus 6. And actually, the sharp bound is due to Shishikura. And it is also 2d minus 2. So except with 2d minus 2 exceptions, you only have repelling cycles. And so maybe let me just give one word on the proof of this theorem. It's a very nice proof. So it's the Fatou's proof is by perturbation. So intuitively, if you take any rational map, so it will have a number of attracting cycles, a number of repelling cycles, and a number of neutral cycles. And if you take a generic perturbation, as soon as you have, of course, what you have to do here is to count neutral cycles. Okay? If you do a generic perturbation, you can expect that it is very probable that half of the neutral cycle will go outside the unit circle and half of them will go inside the unit circle. So if you make a generic perturbation, you look at the neutral cycles, half of them will become attracting. Okay? So this perturbative argument says that the number of attracting cycles, of course, if you take an attracting cycle, I should have said before, if you take an attracting cycle and you make a small perturbation, of course, the cycle will persist by the implicit function theorem, and it will remain attracting. So if you make a small perturbation, attracting cycle remains attracting. And now, if you take a neutral cycle, with probability 1/2, it will become attracting, and with probability 1/2, it will become repelling. So what you get from this argument, of course, if you're able to write it, is that the number of for this small perturbation, you will get this number of attracting cycles, so it is less than 2d minus 2. If you unwind the definitions, you get the bound of Fatou. Okay, so that's the core of Fatou's argument. Of course, it's not very easy to write down explicitly. Okay. So I don't want to say too much about the dynamics in the Fatou set because I don't have the time to do everything. But maybe let me say just one word. So as I said, the point is in the Fatou set when it is not sensitive to small perturbations. Okay? But it might be that the dynamics is complicated. After all, if you could imagine a point with a very complicated orbit, and all the points nearby have also the same very complicated orbit. So there is a very difficult theorem and deep theorem which says that this does not happen. So I will not state it precisely, but let me say that the dynamics on the Fatou set can be understood completely. So you can describe completely the dynamics on every point in the Fatou set. And it is simple. And it's simple. Okay, so you don't have to care about this. So all interesting dynamics takes place in the Julia set. Okay, so now there's a very important object, which is the equilibrium measure. So here I have to state something precise. So there's a theorem, which is due to many people. So it was proved for polynomials by Brolin in the 60s, and then it was proved independently by Lubitsch and a group of 3 mathematicians, Frère Lopez and Magnier. And it says the following. If you take any point z which is not an exceptional point, and you take the measure which is equidistributed at its prime edges. So you take the sum of Dirac masses at the prime edges of z, counting multiplicities, and you divide by d to the n. Then this sequence of measures always converges to something, to some measure mu f, okay, which is an invariant measure, and mu f is an invariant measure. So it is not a course in ergodic theory here, but so I don't want to be too precise on its ergodic properties, but let me say that, so invariant meaning that it's pushed forward under the dynamics is equal to mu, okay? The support of this measure mu is the Julia set. And maybe that it is mixing. So if you don't know what it means, don't care about it. So it means that it has a rich dynamics. Okay, and also it also describes the equidistribution of periodic points. Okay, and also if you take the sum of Dirac masses at periodic points and divide by the right number, the n plus 1, then this also converges to semi. Okay, so you have to think about it as the canonical measure associated with the dynamics. Okay, and it turns out that I don't state all its properties, but it has many important properties. Okay, so let me give an idea of the proof of the convergence. So I will not of the convergence. This convergence here. So I cannot prove this one precisely because it would be too long. But let me. So you see that there's a corollary of this. So if you take any Dirac mass which is not concentrated on an exceptional point, then its iterated pullbacks converge to mu, right? Now, if you take any measure, it is always an average of Dirac masses. So this implies that if nu is any measure such that it gives no mass to the exceptional set, then the same property holds. If you take the pullback of nu, normalize, it will converge to mu. Okay? And so let me prove it for the Lebesgue measure. So I will just prove this consequence here for the Lebesgue measure. So actually what you do is you consider the Fubini-Studi 1-1 form associated to some, okay, so you consider this tautological bundle over P1. You take any Hermitian norm here, a favorite Hermitian norm. It will give you a Fubini-Studi form on P1, okay, and denoted by omega. Okay, so it can be written as, in the notation of Pascal, DDC, so that's DDC, of the log of the norm of sigma square, where sigma is a section, local section of this tautological bundle. Okay? And I consider, so that's a 1-1 form, and on a Riemann surface, 2 form on a Riemann surface provided with a metric, a 2 form is the same as a positive measure, right? Positive 2 form is the same as a positive measure. So actually the positive measure here, in this case, is the Lebesgue measure. And now I take a pullback. What is, so you can pull back this form, and what is it? So of course you cannot find the global expression of it, but if you subtract omega, and you get a difference of 1-1 forms with mass 1, and that's actually, in this notation, the DDC of log of f star sigma. So it's sigma composed with f square over log sigma square, and there is something missing, which is a d somewhere. It's not the same d, right? That's the d of a differentiation and the d of degree. So in coordinates, it's like this. It's 1 over d times the ddc of the log of p zw square plus q zw square over z square plus w square to the d. So this expression, so z and w are homogeneous coordinates, okay, and this expression now makes sense because there's the same degree upstairs and downstairs, so it makes sense to write this expression. And so this is a function on P1, so let's call it, I don't know, this log here is a function which I will denote by G0. It's a smooth function on P1. Okay? And now I can pull back. Now I can pull back. What happens if I pull back this equation k times? So if I take 1 over d to dk fk star of this equation, of 1 over d f star omega minus omega, so of course it is on one side, it is the same as 1 over dk plus 1 f k plus 1 star omega minus 1 over dk fk star omega. And it is also the ddc 1 over d to the k, ddc of G0 composed with fk. Okay? So now I can sum all these identities and get, so by take a sum, and you get this equation, 1 over d to the k plus 1, fk plus 1 star omega minus omega is the sum from j equals 1, so it's 0 to k of 1 over dk, dj, ddc, g composed with f. Let me put the ddc here. G composed with fj. Okay? So I just write this equation. And now, so this function G0, so there was a 0 here. This function G0 is smooth, so this term is certainly bounded by some constant in a uniform norm. Okay, so this series of functions converges in the uniform norm to some function G infinity for the uniform norm on P1. So the sequence of functions, the sum of functions, converges to a certain continuous function. So now this one is only continuous. On P1. And so just by general properties of calculus of distributions, it shows that this sequence of objects converges also to a certain limiting object, which is actually a positive measure. So we get, at the end, you get that this is a sequence of positive measures which converges in the sense of distributions. So the limit must be a positive measure, and at the end, you get that you get a limiting measure mu, which is omega plus the DDC of G infinity. Okay, so this proves the convergence here when you start with the Lebesgue measure. Okay, now what if you start with, let me do it here. What if you start with a Dirac mass? So now, can we analyze this? If you want to analyze this, what you can do is subtract this term, which you know now is converging. So you subtract it like this. And again, this is the DDC of a certain function. Depending on z, which locally is a potential for the Dirac mass at z. So it's something like log z. Okay? And if you want to show, that 1 over d to the n fn star of delta z converges to mu is equivalent. So this term is converging. So you have to show that 1 over d to the n gz composed with fn converges to 0 in L1. Okay? And if you think about it, this is very probable. Because if it does not converge to 0, so I will not give a proof of it because there's a little bit of analysis work to do. But you see that if you want this not to converge to 0, you have Fn has to map, say, a ball in the region where Gz is less than exponential minus d to the n, which is very small. So, okay, I cannot. It is quite easy to see that this, for instance, by Fubini theorem, by the Fubini theorem and kind of Borel-Cantelli argument, you can show that this holds for almost every z. So it is true for almost every z by Fubini, basically. And if you want to attack more complicated measures, you have to do some potential theory. I don't have the time to do the details, but it's not very difficult. Okay, what happens in the polynomial case, which is important? So we saw this morning some potential theory in the plane. So for polynomials, so the Dirac mass at infinity is totally invariant. Okay, so it is more interesting to normalize differently and to normalize by using this Dirac mass at infinity. So if nu is a probability measure, say on C, what you can do is you do nu minus the Dirac mass at infinity. It will be the DDC of some function g and g nu, say, which is subharmonic in the plane with logarithmic growth at infinity. Okay, and you can actually redo. For instance, you can take, take nu, the Lebesgue measure on the circle. Let me call it like this. Lebesgue measure on the circle. What you will have is that Fn star of nu, 1 over d to the n, minus Dirac mass at infinity, it is the DDC of the function log plus of Fn. So f is a polynomial now, Fn of z. And so if I restate this theorem here, let me state it for polynomials. Okay, so so fact, proposition. So the sequence. So if f is a polynomial, the sequence of function 1 over d to the n. There's a 1 over d to the n missing here. Log plus of fn of z converges locally uniformly in the plane to a certain function g, so locally uniformly in the plane C. So it's the same proof as this one with a different normalization. And g, actually, and g is the green function of the Julia set. So I think Pascal explained what a green function is. So it's a continuous function, so it satisfies the following thing. So g is a non-negative function. It is actually continuous. G, okay, let me do a definition here. K is the filled-in Julia set. It is the set of points with bounded orbits in C. So maybe let me do a picture. So for instance, if you take, I don't know, if you take any polynomial, the Julia set will look like that. Kind of fractal set, so that's the Dujardin rabbit. So a typical Julia set for a polynomial looks like this. And the Julia set is the boundary of the set. And the filled-in Julia set is what you get when you get the complement of the connected component of infinity. So that's a typical Julia set for a polynomial. So as I said, the point at infinity is super attracting. So infinity is contained in the Φ2 component. And the complement of this Φ2 component is the set of points which don't go to infinity. So it's a set of points with bounded orbit. And it is called the filled-in Julia set. And by definition, there's a fact that the Julia set is the boundary of the filled-in Julia set. Okay, so the filled-in Julia set is the interior of this picture here, and the Julia set is the boundary. Okay, and G is equal to 0 if and only if on K. So G of Z is 0 if and only if Z is a point in K. So it's a green function, actually, of the filled-in Julia set. And again, to make the connection with Pascal's talk, if P is monic, if F is monic, meaning that F of Z is Z to the D plus lower degree terms, then G of Z is of the form log Z plus small o of 1 when Z goes to infinity, which implies that the capacity of the filled-in Julia set is equal to 1. So there's the Robin constant which is here, and in this case it is equal to 0. Okay? And in this case, let me repeat it again. The equilibrium measure is just the Laplacian, in the usual sense, of the green function. Okay? Okay. So time is almost done. Let me just say a few words. So basically, this is all I have to do in holomorphic dynamics. So that's section 3. Let me say a few words on the non-Archimedean case. So if you take any valued field, so it's a field endowed with some absolute value, okay, is endowed with some absolute value which satisfies the usual axioms. And maybe we have to assume that 0 is mapped to 0. No, 0. Sorry. So you know that in some cases it is interesting to look at non-Archimedean valued field. So let's say it's non-Archimedean. So then most of what I've been saying can be extended to this case. Okay, so for instance, you can, well, maybe not everything, but you can extend a number of things to the non-Archimedean setting. What is complicated in this case is to deal with measures. So it is easy to, at least to define periodic points, to understand attracting or repelling behavior. Fatou theorem is not true. What will be most important to us is that this construction of the dynamical green function is possible in this case. So let me take a few moments to explain. So the green function, so either for polynomials or the rational case, can be defined in this case. So let me say a few words about it, because it is important to define dynamical heights. So if you want to define a green function for rational maps, it is useful to go to the plane, to A2. So take F, a rational map from P1 of K to itself, and you lift it to map from the affine plane to it. So take a homogeneous lift. So then there's a norm, of course, in the plane, which is just the max of the coordinates. And you can repeat the same formula as, so let me state it like this. You can repeat the same formula, so proposition. So you take a lift. The following limit exists. So the limit we can define G, capital F, is the limit of 1 over d to the n norm of Fn of xy. So this limit is well defined. This limit is well defined and it satisfies a number of properties. So it is invariant under F, and it satisfies, it is log of norm xy at infinity. And also it is homogeneous. Okay, and continuous too. So the existence of this function is important. And also, let me not write it again. For polynomials, you have exactly the same formula as this one. So if f is a polynomial, let me just make a remark. So if f is a polynomial, one can repeat the Archimedean case, exactly with the same formulas. Okay? And so the proof is not very difficult. There's one point. So my time is over, so let me be quick. There is one important point of the proof, which is the analog of this continuity of the function g. And the point is this one, is that, so the main point, is that there exist two constants, C1 and C2, depending on f, such that f, the norm of f of xy, divided by norm of xy to the power d, is controlled between C2 and C1. And these are positive constants. So let me say that it's a number field. Let me say that K is a number field endowed with some norm, either Archimedean or not Archimedean. So this estimate is true, so the upper bound is obvious. You just look at the coefficients. For the lower bound, you need to do something. So in the Archimedean case, the lower bound is just due to the compactness of the sphere. Here you must use some algebraic arguments, and actually this is a consequence of a Nullstellensatz. Okay, the existence of this lower bound is consequence of the Nullstellensatz. And then you can write this green function here as a convergent product. So I did sums because I used logarithm before. And here you just write a product of functions, and using these bounds, you get that this product is convergent. Okay? So it implies that these green functions also exist at non-Archimedean places. You can actually also give a meaning to this, to what it means to take the Laplacian of this green function, which is more complicated. It uses this Berkovich space technology. But what is important is to know that such object exists, because when we will do in the next lectures equidistribution of small points, it is useful sometimes to decompose the canonical heights as a sum of local factors. And the canonical height will be defined by taking sums of these green functions at all places of your favorite number field. Okay, I think it's time to stop. Let me just check. Okay, I think I can stop here.